The conflict in modern hypercar powertrain engineering is often presented as a zero-sum game, massive displacement versus forced induction, or the traditional internal combustion engine, battling the surge of electrification. Yet, this simplification misses a far more fundamental battle. The war on weight every gram shaved off the chassis or the engine block translates directly into increased responsiveness and superior dynamic performance. For decades, the high horsepower segment was dominated by the V8 or the V12 established architectures that promised output, but always came with the heavy toll of mass, complexity, and physical size. This was the unspoken engineering problem: how to deliver the expected mega power of a hypercar without carrying the weight penalty of conventional architecture. Koenigsegg, the specialist engineering house from Ängelholm, Sweden, answered this challenge, not by adapting an existing V8, but by fundamentally reimagining the very concept of the performance engine. They introduced the Tiny Friendly Giant, or TFG, a 2.0-liter three-cylinder engine designed for the four-seater Gemera. On paper, a three-cylinder unit belongs in a compact commuter car, not a mega GT, but when we analyze the patent filings and factory footage, we see that the TFG is a textbook example of engineering. Adaptation, pushing past constraints. The goal was 600 horsepower, meaning a world-beating 300 horsepower per liter and a dry weight of just 70 kilograms. This power density defies conventional physics, or at least conventional valve train design. The core problem this engine solves is the inefficiency inherent in the traditional camshaft. In a conventional engine, fixed camshafts dictate when the intake and exhaust valves open, a compromise that is never ideal across the engine's entire operating range. The TFG, however, is the production culmination of the revolutionary Freevalve system. This technology removes the camshaft entirely, replacing it with pneumatic hydraulic electric actuators that control each valve individually. When we analyze the combustion cycle, we see that this freedom allows for infinite, optimized timing and lift. This adaptation is the secret to the TFG's incredible thermal efficiency and its astonishing specific output. It allows the engine to run complex cycles like high-speed scavenging or cylinder deactivation, moments that would be physically impossible with a fixed mechanical connection. It is the engineering equivalent of cutting the anchor line. Now let's open the factory blueprints and deconstruct the story of this engineering titan. The journey from a digital model of the TFG to a functional 600 horsepower reality involved a manufacturing hunt focused entirely on precision and extreme materials science. The challenge was twofold: integrating the high-performance core with a structural body and ensuring the complex Freevalve actuators could operate reliably under the immense heat and pressure generated by such extreme power density. This is where the narrative moves from theoretical design to hands-on, meticulous construction on the factory floor. The engine block itself is a compact, deep-skirt design crafted from aerospace-grade aluminum. However, achieving that impossibly low 70-kilogram weight required integrating high-strength, lightweight components wherever possible. Factory footage shows the so delicate application of pre-impregnated carbon fiber for components like the intake manifold, which is not merely a weight-saving measure, but a thermal management decision. Carbon fiber's low thermal conductivity helps isolate the dense charge air from the engine's high operating temperatures, contributing directly to the engine's power output. This is a critical element of the manufacturing process, using materials not just for lightness, but for their specific physical properties in extreme conditions. The heart of the manufacturing complexity lies in the Freevalve system. Unlike a conventional head assembly, which is precision machined for the camshaft bearings, the TFG's head must accommodate an array of custom, high-speed actuators. Each valve position requires an electromagnetic sensor, a high-pressure pneumatic line, and its own dedicated microprocessor control loop. This system replaces the hundreds of moving parts in a traditional head, cams, followers, springs, rocker arms, with a highly optimized, high-frequency mechatronic assembly. The precision required in aligning these actuators is measured in microns, far exceeding the tolerances of standard automotive manufacturing. We see in the build process that the mounting points for these actuators are often finished using 5/8 CNC milling, achieving the kind of precision usually reserved for Formula 1 power units. Furthermore, the design itself incorporates a sequential turbocharging arrangement to manage the high exhaust gas energy. A smaller, quick spooling turbocharger operates at lower engine speeds, followed by a larger turbo for the top end. The precise switching between these modes is facilitated by the Freevalve system's ability to manipulate exhaust pulses, effectively eliminating turbo lag and ensuring a flat, usable torque curve across the rev range. This is a fundamental, comparative engineering advantage over traditional engines of similar displacement, which often suffer from a narrow power band or significant inertia. The TFG is not merely powerful, it is dynamically flexible, engineered to perform optimally in its designated role as the primary high-output component within the Gemera's sophisticated hybrid powertrain. The intricate wiring harnesses and integrated sensor arrays required for the Freevalve's control unit transform the engine from a purely mechanical device into a highly intelligent, self-optimizing system, a manufacturing step that dramatically increases assembly complexity but unlocks performance previously confined to the theoretical realm. The success of this hunt lies in the flawless integration of extreme material choice with next-generation electromechanical valve-train technology. The delivery of the TFG installed in the chassis of the Koenigsegg Gemera represents not just a technical breakthrough, but a powerful statement about the future of high-performance internal combustion engines. This unit, paired with 3 electric motors, forms the backbone of the Gemera's 2,700 horsepower hybrid system. The TFG is centrally mounted, acting as a structural member within the Hypercar's carbon fiber monocoque, a testament to its rigidity and compact form factor. Its astonishing performance, 600 horsepower and 600 Newton meters of torque, ensures it is the primary power source, even as the electric drive units provide supplemental fill-in torque and instantaneous thrust. When we analyze the resulting performance metrics, the engineering adaptation is immediately justified. The Gemera is a 4-seater, a grand tourer, yet it possesses acceleration figures that rival dedicated 2-seater hypercars. This is the ultimate myth-busting application, proving that massive cylinder count is irrelevant if thermodynamic and volumetric efficiency are pushed to their absolute maximum. The TFG's ability to run on various fuels, including E85 biofuel, further highlights its innovative design, showcasing the potential for near-zero emission hypercar operation while maintaining extreme performance. This leads us to the technical legacy and the market niche the TFG carves out. By shedding the weight and size of a conventional V8, Koenigsegg created space for the batteries and electric motors necessary for true Mega GT performance without compromising the cabin size or the vehicle's overall weight balance. This engine is a cornerstone of the future hyper-hybrid architecture, demonstrating that the future of extreme power is not the replacement of the internal combustion engine, but its radical optimization and downsizing. It proves that the relentless pursuit of volumetric efficiency through technologies like Freevalve, remains a viable path for the highest echelons of automotive engineering. The tiny friendly giant is, therefore, not an endpoint, but a foundational blueprint for how elite manufacturers can achieve performance parity with electric drivetrains while maintaining the unique mechanical and acoustic texture of a high-revving, high-output engine. The Gemera, powered by the TFG, defines a new market, NEEC, the family-friendly Mega GT that makes zero compromises on velocity or engineering. Purity, the intricate processes that went into forging this small yet monumental engine, the meticulous fiber layup, the micron-level calibration of the Freevalve actuators, the sheer nerve required to bet on a 3-cylinder architecture, reveal the depth of human ingenuity. It forces us to pause and truly appreciate how engineers relentlessly question established rules, transforming audacious concepts into metal and carbon reality. The TFG stands as a brilliant reminder that in the apex of automotive engineering, size means nothing and efficiency means everything.